This video introduces correlation and related concepts and goes with chapter 15 in your textbook. So first, we need to define what a correlation is. And I know that sometimes people use correlation in casual conversation without quite understanding what it means in terms of statistics. So what we're talking about with a correlation in terms of statistics is that two variables relate together. They relate in some sort of way. As one variable changes, so does the other, either in the same direction or in opposite directions. So the two variables are usually some kind of scale variable, an interval, or a ratio variable. And the really important thing that people need to understand with correlation is that just because two different variables are associated with each other does not mean that one causes the other. So for example, if you said that, and actually there is a correlation between ice cream sales and murder rates, for example. Now, that doesn't mean that people buying more ice cream cause them to become murderous, or that people drown their sorrows because of somebody getting murdered by eating ice cream. It doesn't mean that one causes the other. It just means that there's some sort of association there. A correlation coefficient is a statistic that quantifies the relationship between two variables, and it can either be positive or negative. The range of a correlation coefficient is from negative 1.0, which is a perfect negative correlation, and 1.0, which is a perfect positive correlation. Now, the value of the number, not the sign, so not whether it's positive or negative, indicates the strength of the relationship. And the closer the value gets to either 1 or negative 1, so you could think of it as the further it gets from 0, the stronger the relationship. So a positive correlation is when the relationship between two variables is that when one person has a high score on one variable, they also tend to have a high score on the other variable. So it's a direct relationship between variables. You could look at it, things like SAT score and GPA, for example, would have a positive correlation. We would also see a positive correlation in weight and height. Maybe not as strong, but we would still expect that taller people would also be heavier people. A negative correlation is an association between variables where if people have a high score on one variable, they tend to have a lower score on the other variable. So it's an inverse relationship. Here we can look at nights socializing per week and people's GPA and see that the people who go out more often have a lower GPA. We could also say that an inverse relationship exists for heart rate and body mass. So if you've ever held a mouse or a baby, they have much faster heart rates than, say, your dog or another person who's an adult. And so there's a negative association there. This is an example of a perfect positive correlation. This would be a correlation of 1.0. And the reason I would say this is because we actually can draw a straight line through all of these dots, just like this. We draw a straight line through all the dots, and it's not perfectly straight, but close enough. Those dots all fall on the line. There's no error. We can perfectly predict. We know exactly what score you're going to get if you have 2 absences from class. And this is funny because the more you miss class, the better your exam score gets. I don't know how often that actually happens. Here's a perfect negative correlation. This would be more likely, right? That if you didn't miss class at all, then you would get 100, and if you missed class once, you would get an 80, a 90, twice you get an 80. So that's a perfect negative correlation. Again, we can draw that straight line through those points, and there's no error. Those dots don't fall off the line at all. So we also have guidelines from Cohen about how strong a correlation is from using the correlation coefficient. And we usually don't in social science research find very high correlations. If you get a correlation of 0.50, that's really strong. Um, but here we see that a small correlation would be a correlation coefficient of 0.1, a medium of 0.3, and a large of 0.5. So let's check your learning. Which correlation is stronger? A correlation of 0.25 or a correlation of negative 0.74? If you said negative 0.74, you'd be correct. Because remember, it's the magnitude of the number, the further away it gets from zero, that determines how strong a correlation is, not whether it's positive or negative. Okay, before we get to hypothesis testing, which will be covered in a separate video, we need to talk a little bit about misleading correlations because oftentimes people have a hard time either understanding what a correlation is actually telling us or um, thinking about correlations in the appropriate way. So here's something to think about. There is a 0.91 correlation between ice cream consumption and drowning deaths. So, does this mean that eating ice cream causes people to drown? Or does grief cause us to eat more ice cream? Think for a moment and come up with an answer. Well, if you said that neither, then you are correct, because correlation is not causation. There can be invisible third variables. We can say, right, so if A were eating ice cream and B were drowning, then you could have a direct relationship. That could actually exist. Same thing for drowning causing eating ice cream. But there's usually a third variable that's really responsible for some of these kinds of relationships. So in this case, what do you think that third variable would be that has something to do with ice cream sales and drowning? If you immediately thought of, well, when it's hot outside, hot weather, people go swimming, people eat ice cream, well, then that would be a good third variable. So sometimes we have spurious relationships, which means that we see relationships among variables when it's not really that one variable is directly related to the other, that there's some association, but it's really actually explained by a third variable. Another issue that comes up with correlation is a restricted range. So if we only look at a small portion of the full range of data on something, then it could obscure the relationship. So if we look at this particular set of data, we have the number of hours studied and we have ages here across the x-axis. And it looks like you might be able to fit a straight line in there somewhere. Well, what happens if we only look at 22 and 23 and through 25-year-olds, that upper half? Well, that strength of the correlation is not even significant. It looks like there's no correlation at all. So we need to be careful that we have the full range of data instead of a restricted range, because it might weaken the correlation and make it seem like there really isn't a relationship when in fact there is. The other thing is that outliers, see this guy over here, somebody who spends a lot of time talking on the phone, but also somehow spends a lot of time studying. Usually you wouldn't expect to see that. So here's one person who studies and uses her cell phone more than anybody else. And it changed the correlation from 0.14, a negative correlation, to 0.39, a very strong and positive correlation. So outliers can have a significant impact on what the data are, because if you think about where a straight line would fit, it would probably be like this. But if we didn't have her in this sample, then you can kind of see that there might be a negative relationship here. Okay, so the Pearson correlation coefficient is a statistic that quantifies a linear relationship between two scale variables. And we symbolize that with the italic letter R, which is a statistic based on sample data. But we use the Greek letter rho when it's a population parameter. And this is the formula for our correlation coefficient, which I will talk a little bit more about in the next video when we talk about how we use correlation in hypothesis testing.